My name's Jeff Hamann. I have a small startup down in Corvallis called Forest Informatics. A little bit of background on this presentation is when I originally wrote the abstract for this thing, I thought, you know, it would be great to put it in a very tongue-in-cheek kind of environment like the Lorax versus the Onceler. And I don't know, does anybody remember the story of the Lorax from Dr. Seuss? It's okay if you don't. I didn't really remember the actual story until I submitted the abstract. In 1971, which I believe was the same year that the first email message was sent, Dr. Seuss wrote a cautionary environmental tale called The Lorax. And the premise of the story is the Onceler, which was this kind of environment, you know, this business-oriented entity comes to town. You never actually see his face. He's just the greedy little hands at work. And he starts chopping down all of the truffula trees to make thneeds that nobody needs. And as soon as he chops down the first tree, this little fluffy, cute guy pops up called the Lorax. And he stomps his feet and says, I like the trees, you need to stop cutting down trees, etc. And the story goes on, and the more trees that get cut down, the more the Lorax gets hacked off, but he actually doesn't do anything except for talk to the Onceler. And halfway through the story, the Lorax splits. He just picks up and leaves and goes off to some greener pasture after all the trees have been cut, and the animals leave, and the brown barbaloot bears bail. So I thought, wouldn't it be interesting if you could create sort of the analytical engine that the Onceler uses and give it to the Lorax, so that the Lorax can combat the Onceler using his own terminology, his own language, and demonstrate to the Onceler the shortcomings of his thinking. So, so what I did is I cobbled together this very simplistic geospatial analysis stack that focuses on a field that I specialize in, which is forestry and forest operations and forest management. I thought, okay, I'll run up the flagpole, so here I am. So what I'd like to do is really quickly present, you know, what the stack includes, describe some of the tools that are in there, give some of the pros and cons of each one. I'm assuming that a lot of you folks are probably already familiar with parts of it. And so I'm going to kind of blast through that as quick as I can, show a little example of what someone like the Onceler would use to determine how fast to cut down trees, etc. Go through a little report generation exercise using some of the more popular open source tools, and kind of wrap up in the end. So a little bit of kind of factoid backgrounds. 1.6 billion people actually depend on the world's 10 billion acres of forest for their livelihood. 300 million people actually call it home. So 300 million people around the globe actually live in forests. It's habitat to about 2/3 of the planet's species. I'm going to caveat that with probably 2/3 of the terrestrial species, but I don't know for sure because I pulled these out of, I want to say I pulled these out of The Economist, but you know, there it is, it's in The Economist, so it's got to be realistic. The globe's forests and their soil contain about over 1 trillion tons of carbon. That's about twice that's what's in the planet's atmosphere, and it accounts for about $300 billion in trade annually. Unfortunately, every year we lose to deforestation about 130,000 square kilometers, which accounts for about 20% of the globe's greenhouse gas emissions, and accounts for about 100 species lost per day, just go extinct. So, as you can imagine, there is no shortage of controversy or lawsuits going on, and the ability to provide some kind of realistic analysis that builds trust on all sides is critical. So, you know, I thought my challenge was, and I call it a challenge because basically I have a tendency to not do something until someone says, I bet you can't do it. So what my challenge to myself was, is it even possible to create a self-contained analytical engine, platform, set of gadgets? I use thingamajig and whatchamacallit a lot, which I know is probably not cool in the software community. But can we actually build an analysis stack? Can we use it for you know, the extract, transform, and load process? Can we use it for report generation? Can we use it to create an archive of the entire process that we've done for the analysis part? And as a kind of a science nerd engineer type, can I use for doing literate programming? Can I use it for repeatable research and merge the text and the analysis in the same kind of document and do it on other data sets? Can I repeat it on the same data set? Ultimately, what would be swell if I could use it to build a court-admissible, audit-compliant, rock-solid, yes, I've done my homework, and this is the best scientifically based decision that we can make about managing forests of all kinds. And can we do that in a transparent way? And so far, the only tool set that I've found that allows me to do that is open source software. The community loves the concept of transparency, and that's very important for this kind of task. And ultimately, can we make it a kit or a platform that we can put on little boxes that bolt onto the side of foresters' pickup trucks? Can we put them in sawmills? Can we do all of the sorts of things that are completely in the antithesis of what natural resource professionals behave like? We have some very common rules, like if it doesn't run on diesel, I don't trust it. If it doesn't have brakes, don't write it. And if I can't understand it, I get to throw it out. Because we use tools that are 100 years old, and we like it that way. So here's the basics of the stack, and this first chunk here just focuses on the foundation of the stack, right? So for this, I kind of decided to go with FreeBSD for the basic operating system. I picked it because it seems to be engineered and not grown. And that is not a dig on Linux. It's that I found when I started playing around with open source software about a decade ago that every new flavor of Linux that would come out, I had to relearn paths and infrastructures. And with FreeBSD, they seem to maintain a militant adherence to file systems and the structure. PostgreSQL and PostGIS provide the persistent data storage with geospatial capabilities. Proj4 and Geos give the ability to reproject data back and forth between different coordinate systems and projections. Geos provides geometry, and I'll talk a little bit more about these in a second. So the GDAL OGR library provides, it's like the Swiss Army knife for data translation. I'm a huge R guy. I've written a couple of packages in R. In fact, I wrote a book on forest analytics using R, and using a lot of the techniques that I present here. PLR, which is an incredibly awesome tool written by Joe Conway of Creditive that allows folks to write stored procedures in R, and I'll describe a little bit more about that later. And I use LaTeX, and then SWeave and Tangle for doing report generation and the literate programming part. So I like FreeBSD simply because it's rock solid, and you can't go wrong with the mascot as cute as that, although I've been told that it kind of freaks some folks out. And when I say BSD, I really mean the whole family of BSD. I mean OS 10 because it seems to be a pretty face on top of FreeBSD. I have not personally used NetBSD or OpenBSD, and if any folks here have experience with those, I would love to sit down and talk to you about it. But so far, my thinking is that it probably really shouldn't matter because the analytics part is the critical part. So the description of PostgreSQL, it provides ACID-compliant persistent data storage, which is a great, well, I guess it's a requirement, not a feature. And you can pretty much extend PostgreSQL with anything under the sun. So it you can do procedural language programming. It has different data types. You can overload operators and all of those goodies. You can write interfaces, or excuse me, you can write in interfaces in pretty much any one of your favorite languages. Unfortunately, I work with, I don't see anyone under or over 60 in here. I work with a lot of old folks. And when I say old folks, I mean folks that are within 5 to 10 years of retirement, and they love Fortran. Lots of it. So unfortunately, part of this whole stack requires Fortran, and that's just the conditions that I'm given. So to provide the geospatial capability, PostGIS is a great add-on for PostgreSQL. It comes with about 800 functions for doing coordinate system transformation, long transaction support. If you have geometries, two polygons, if they're far apart, they're not tangent, if they're touching, if they're overlapping, and a lot of the vector type functionality that folks who do geographic information systems rely on. So it does require the proj4 and the geos libraries for managing the spatial reference system and for doing the geometry operations as well. And so here's the take-home message with PostgreSQL and PostGIS. And I'm speaking most of what I speak today will not be software-centric, I don't feel. The take-home message is with pretty much nothing but proj4 and geos and the spatial reference table that comes with PostGIS, you can translate this byte string representation of a point at 0, 0 with this spatial reference identifier in the spatial ref table to somewhere on the globe, and vice versa. So it removes the drudgery from a user's perspective of translating geographic information into table form and back out. So if you were an old ArcInfo user, any old ArcInfo users in the room, there were pretty much like 3 modes. There was Arc, Grid, and Info. I was the Info person. So the geometry and all of that information was kind of secondary. So, okay, so we've got the fundamental stack. The GDAL OGR is essentially the Swiss Army knife for translating one, and I'll use the term loosely, file type into another. And so there are about, the GDAL works for the raster components, so if you have satellite imagery or air photos or things that are raster data, that's what that's for. The OGR works for the vector, and most of the time I work in vector because I'm doing scheduling and management support functionality. So there's about 100 raster formats and 40 vector formats. And by the way, I don't know if folks bothered to download this thing before the presentation today, but I have put links to a lot of this stuff in there. So if you look at the presentation and there's something that you're more interested in, just click on the word or kind of hover around and see if there's something in there that shoots you off to where you need to go. So here's an example of loading data into PostgreSQL database using the OGR to OGR function. So we're going to just overwrite what we have there, and the file format output is PostgreSQL. There's our connection string. This is an ESRI shapefile. And so you run that from the command line, and a la peanut butter sandwiches, all of your data gets slurped into your database. So I mentioned before I'm an R guy. It is got an installed user base of, I believe, 1 to 2 million users. So its primary function is for doing statistical calculations and math and visualization and drawing pretty graphs. And the way I came to it was escaping SAS. So it made pretty graphs where SAS didn't, so I thought maybe I'll start using that, and I don't have to pay enormous fees to use it. The nice thing about R is it works independently of all the other packages in here, and it has a lot of interoperability with some of the packages that I'm talking about. So if you have a relatively smallish project that you don't need to load a lot of data into PostgreSQL, you can do it directly in R. So you can do some of the geospatial processing, you can do the coordinate transformations, and it works pretty well. I use the map tools in spatial a lot because I do a lot of kriging or spatial interpolation for productivity measures, and it works great. Some of the problems with R are that it requires all of the data to be in memory, and we've seen some presentations here about possible workarounds for that kind of thing. So, I mentioned a little bit earlier, we've got a thing like PLR that Joe Conway created that has been a lifesaver for being able to create analytics stuff on your local client machine, and then later be able to upload it onto the server. So you kind of do your thrashing and hashing about on a smaller data set. You kind of get the process down, you lock it down, and then you put it up on the server, and you can lock it into a stored procedure. So some of the problems with it are is it's a little bit difficult to debug because everything's going on way off in the cloud, or not the cloud, in Neverland I call it. And so if a regular user stumbles across some problem, you have to kind of come to the rescue. Okay, and for the reporting system, I don't know all of the possible reporting environments out there now. I'm a LaTeX guy, I'm a control freak, and I'm okay with that. So if you've done scientific writing for journals or produced technical manuals, eventually you will bump up into LaTeX. From what I've come to understand, it's pretty much the de facto standard for science folks for doing technical writing. The lifesaver for me was the automatic generation of the bibliography. If you have to succumb to graduate school at some point, writing a 12-page bibliography is probably, it's one of those make it or break it kind of deals. LaTeX, you just put the tag in, and I use it from within Emacs, and so it's great. It automatically generates the entire bibliography, and you can tell it, well, I don't want it formatted for this journal style, I want it formatted for this journal style, and you just change one argument, and poof, everything gets formatted correctly. But the takeaway message for me is, so far, most of the work that I've done with people with LaTeX has been they get in there and they write as a human for other humans. So, so far, in terms of this stack, this has been where the Achilles heel has been, because we have to front load all of this knowledge that we put into the document. And what would be nice is if we had a system where we could take analytical parts and simply plug those into the report and generate those automatically. So, if you're not familiar or comfortable with building stuff from source, here's pretty much in a peanut shell how to build something from source. So we go into the blah 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 project and grab the blah 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 tarball, unzip it, which is always funny because we're dealing with tarballs. See, you have more than one process. The -J argument, make check, make install, and then the easy target, which I'm still waiting for a software project to make life easy. This is usually the first error that I get whenever I try to build anything for the work that I do. Is can't find a Fortran compiler. So I don't mean to be dismissive, and it's okay to not raise your hand. Show of hands of people who don't know what Fortran is. Okay, sweet. So out of curiosity, if anybody's interested in looking at kind of the parts for this thing, I've included a makefile on my website. You can go and download this stuff for. Here's an example after running configure for R. So configure with blah, blah, blah. If you want to put in all your special little tools and libraries, you can do that. It's, I think this thing coughs up like 4 different compilers it requires. Includes, some basic library kind of stuff, and it includes a bunch of recommended packages. It would be nice to know what those recommended packages are here, but it doesn't, so I'm not going to complain. And if you want to run it for the first time, here you go. This is from the command line, and up comes this little screen. And this is one of the things that I run into quite often with new folks in these tools. R is free software, and they go, awesome. Comes with absolutely no warranty. Whoa, 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 whoa. Wait a minute. So, because a lot of folks might be in a corporate environment, and the idea that you don't get a warranty with something freaks them out. They forgot about the fact that they aren't paying for it just yet. And it's nice because it kind of comes with all of this basic, how-to demo type stuff. So, if you get in there, the first thing you should probably do is demo graphics. A bunch of pretty graphics fly up. You go, oh, sweet, I want to do that. I actually get a lot of requests for people who email me an example of a plot they see somewhere else and go, wow, I want to do that with my tree data. Completely irrelevant of whether or not the data is appropriate to the representation graphically. So apparently the pastel colors that come with R are they're kind of a little hook. Okay, so got the basic stack, pretty painless. So let's take a look at using it for some really basic examples. So what I've done here is I've downloaded from the Washington Department of Natural Resources some actual data on the forest practice applications. So if you are a forest landowner in the state of Washington and you are subject to the jurisdiction of the Washington Department of Natural Resources, you have to either fill out a PDF or go online and file your forest application, forest practice application for anything like planting, partial cutting, clear cutting, fertilization, road construction, herbicide application, pesticide application. I don't know if you have to do it if you want to feed bears, but that was something that we used to do. Go out with 5-gallon buckets and throw out Purina bear chow. And so here's a plot that's just in Google Earth of all of the past forest practice application polygons since 1996, which is, I believe, when the DNR started cataloging this stuff. So there you have it. You notice that there's big gaping holes on federal lands, so they're not subject to this. And like here's the Spokane Tribe Reservation. Tribal reservations are not subject to these requirements either. And then this little white blotch of dots is something that we'll look at a little bit closer here in a few slides. But that is an example little forest that forestry students are often using to learn how to do linear programming, mixed integer programming, look at policy constraints and adjacency constraints and that kind of stuff. So this is a close-up of that little forest. And the original data for this forest, I didn't have the spatial information for, so I just made some stuff up. And it includes 8 stands. A stand, for all intents and purposes for today, is an area of continuous, homogeneous forest type, which this is clearly not. But I needed a way to represent 84,000 acres worth of forest in a small slide. So, before we had that just big smear of red all over the place, these are these little tiny polygons here. I don't know if you guys can see that in the back, but these little tiny ones are the individual polygons for the historical forest practice applications. So, Southwest Washington, in fact, all of Western Washington is abuzz with forest activity, and you can see it there, which is, I think, one of the few states that actually publishes this information. So you can intersect this with landowner information and all that kind of stuff. So here's a script, just a real kind of tongue-in-cheek script of the whole process so far. We've gone and downloaded some data. This is the actual URLs for the data. We've created a database, and I just called it OSCon 2011. I'm hoping everyone that's giving the presentation did not call their database OSCon 2011, but I'm not going to worry about that right now. And then we add the PostGIS capabilities. So we add the spatial capabilities. We throw in all of the, I want to say there's like 3,100 spatial reference system strings. And then I add the PLR capabilities that allow me to write stored procedures in R. Again, using OGR to OGR to simply just ingest the 2 data sets that I presented. And I have a little SQL file that does some checks, and we'll take a look at that in a sec. And then finally, once all that stuff's done, you can make a report with something like this straight from the shell to generate your SWeave, which produces a LaTeX file. Okay, so here's just a real quick example of what some of the data looks like, and we don't need to focus on this too much, but this is from the FBA. This kind of thing is one of those things that just becomes an annoying bit of cruft, right? So this was a shapefile, an ESRI shapefile that was downloaded to my local box, and those things always seem to have an area and perimeter in them. Interestingly enough, there's like 50 fields in this file. All the field lengths are 8 characters, so we get a lot of this kind of stuff. And here we have the geometry. So now we actually have 2 pieces of disparate information. We actually have the geometry as byte representation in PostGIS, and we have old values that came from the legacy data. So these can actually go away. They're an artifact of the incoming data, which does 2 things. It makes a nice check to make sure that you are using the right units when you're reporting. And it's just nice to have some number to hang your hat on, because when the analysis folks that I talk to say things like, well, how did you calculate the area? Well, how did you calculate the area? Well, I used the GIS. Well, so did I. And so unless you are producing the exact same numbers that they are, they start to get nervous. So this is great because here's the smaller forest, the white boundary forest. Right, so now the actual geometry is tagging along with the data. Okay, so here's a real, by the way, I am not the greatest SQL programmer. So if anyone has hints and tips to make these a lot cleaner, please see me after. So I'm just using a simple view as a check to figure out what I'm just ingested and produced. So I'm pulling the year out. So this is a PostgreSQL function to get the year. I'm just counting up all the clear cuts. I'll get to that in a sec. And this function right here is an example of the PostGIS calculating the area. Right. So the field is the geometry, well-known binary. I calculate the area, which normally returns in the native units. Divide that by 43560 square feet per acre, which is a number that is tattooed on every forester's brain. And I'm also summing up the area and dividing by 9.8 million, which, where did I get that number? I pulled it off of a website that said, you know, there are 30 million acres of forest in the state of Washington. Some of those are federal, some of those are reservation, so you don't really need to focus on those. And I just put this in here as an example. I wanted to look at all of the forest practice applications that were approved for operation, and I only wanted to look at even age units, which is code for clear cutting. And group them, order them, and so this is the resulting table. So we can kind of take a look at how many clear cuts occurred in the state of Washington, or for approval, I should say. And these are the acres. So, you know, in 2006, we had 2,668 clear cuts and cut about 94,000 acres. And so I'm interested in things like the relationship between housing starts and forest operations. You could use this kind of information for that, and this percent of the land base is just a number that I calculated for example. So sometimes we were harvesting more than 1% of the land base per year, sometimes a lot less. Right now we are almost at the end of July, and we are about halfway through what would be kind of considered a normal level of harvest for this data set. Okay, and our smaller forest that we'll kind of look at a little bit more in our harvest scheduling analysis here in a sec. We have 8 stands, 5,000 acres for the first 4, all that kind of stuff adds up, and we start to see a little bit of stuff like this. For the most part, I think folks here are pretty comfortable with things like having this little tiny bit at the end, because we are taking data off of the web. We're not going out with high precision surveying instruments and getting ridiculously high closure rates on the traverse. That's okay. But it tells us that yes, we've actually ingested all 84,000 acres, so we can proceed with the rest of it. The thing that I do a lot is generate yields for scheduling and forecasting. So this is just one more piece of information that we would need. For example, for that first stand in the first period, it's 30 years old and would produce, for every acre harvested, about 3.2 volume units. I believe these are like 100,000 cubic feet per acre. So if we don't harvest it in the first period and we wait till the second period, which makes it 40 years old, 10 years out from now, we get about twice that. So remember my dig on Fortran before. Excuse me, let me back up a sec. So for just intents and purposes, right now, I'm just displaying the volume. I've worked on projects where the number of metrics that we generate for a particular stand over time can be up into the several hundreds. I've worked with scientists who believe that we should have 8 different age metrics for trees and stands. And being able to archive that process has been challenging. So for doing growth and yield, for the most part, federal agencies use a thing called FVS. It is this ginormous pile of Fortran code that for most modern software folks has been defined as incomprehensible. And it works. They like it. So I'm not going to mess with it. As long as I can compile it and kind of thrash on it a little bit, I can generate all the age or all the yield tables that people expect to see. Okay, so we've managed to blast through, getting some inputs. You know, we've tested some of the metrics. We've just looked at some like macro scale stuff, and we want to apply it to our little forest. So now we're going to take a look at using R and PLR to do some basic optimization. And so, and when I say optimization, I mean the kind of optimization that you know, corporate types and people who need to create even flows of cash or volume or jobs create. So, and then we can, you know, once we've done all this, and in fact right now we could spit those geospatial attributes back out for you know, consumption and news or feeds or things like that. So here's our forest again. So, and I know you're not supposed to show math and equations in a presentation, but for here I need to, because this is possibly the smallest example of a linear program that's applicable to forest planning that I could get my hands on. So I'll just blast through this super quick. So here's an example of, we want to maximize our objective function. So if we're calling from our yield tables, if we had 1 acre of harvested from stand 1 in period 1, it would give us 3.2 volume units. If we harvested an acre from stand 1 in period 2, it would give us 6.1 volume units, and so forth and so on and so on. Now this one only has 8 stands. It's not uncommon to have 50, 150, 250,000 stands where the area is about, you know, from 1/4 to 2 acres in size. We've got some constraints, so subject to some constraints. Here we want to, since we're doing what's known as a strict area control, which means thou shalt harvest the exact same number of acres from the landscape over the planning horizon in perpetuity. So we need to include some physical constraints here. You know, add up all the acres that we cut from stand 1 in period 1, stand 1 in period 2, and period 3, yada, 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 yada. 5,000 acres, right? So you can't cut more acres than are actually there for all 8 stands. And then we have some policy constraints. And so, you know, we get down to the bottom, and we've got, okay, take all the area that we've harvested from stand 1 in period 1, 2, 3, 4, or stand 8 in period 1, stand 7 in period 1, blah, 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 so that we have an exact equality constraint of 14,000 acres, okay? So, okay, pain's over. So to do this, I use GLPK for doing linear programming, or for solving linear programming, I should say. It comes with a great math programming package that I have started to become accustomed to. So the process that most of the time I use is prototype the analytics in R, because you can just kind of hack and thrash on it, and then go through it, and then once you create a solution and you've archived that whole thing and you've puked out your output files and your reports, you may or may not want to repeat this process on other landscapes, and you can put that in PLR. But here's an example of using GLPK, using the GLPK package for R, which gives you an interface to the solver. So here we create a problem. We give it a name, we determine which direction, because sometimes optimization means minimization. And there we go. So now, I just screamed through a lot of stuff. I gave a presentation with Joe Conway at PG West last October, November, and I spent 40 minutes presenting what I just blasted through in 3 slides. So if there's a lot of holes in what I just said, I apologize. But here's kind of the nugget of the whole section. Up in here is all of the code that would normally have been for generating the yields, formatting the data, creating the matrix that we're going to solve in the solver, and then we run the solver and we create some little chunk of code here, and because ultimately what we want to do is actually come up with a useful solution for a practitioner. So this part right here is simply reformatting what comes out of the solver, okay, so that we can create a table. The PLR part, yes sir?
I'm just wondering if you could show that previous slide just for a second so we can get a picture.
Okay.
Yeah, that's great.
And you can download this too.
Thanks.
Okay. So the beauty of something like PLR is it allows you to essentially take your entire R function, strip out the top and the bottom line, and stick it in here, and replace it with, you can have it return like a table definition, and I just called it harvest, and I'll show it on the next slide. And if you're familiar with R, you get these, you use these things called data frames a lot, which are just analogous to database tables. So you can return that thing with, by creating your function PLR, and you get something like this. So what this tells a practitioner is, okay, I'm going to just select everything from this function, which spits out a record set of harvests. And so in period 1, we're going to harvest 12,000 acres from stand 7. So this gives the inputs that you can start doing your checks on, where before we would just get this ginormous matrix of stuff out that was essentially incomprehensible. So, and we can then just use the same kind of SQL techniques to check our policy constraints, and here they're all the same for all the periods. So we know we've actually, one, got a good solution, and we can figure out what our wood flow is from that. So, which is good. So, okay, that's all fine and dandy. We've done the basic stack, we've done some basic analytics. Now it's time to make reports. And that is quite possibly the most time-consuming portion of many of these projects. There's lots of ways to do it. Some folks do it directly within R. Some people use Excel. Some people use Word. Some people don't do it at all and just write it on the back of a piece of paper. You can view your results in QGIS. But since I'm a LaTeX guy and I like SWeave, I'm going to start with the report generation. I'm going to use LaTeX for report generation. So when I have to work collaboratively with other science types, here's the process. Hey Jeff, I got a proposal I want to do, blah, 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 yada, yada, yada. I'm going to send you a Word file. Can you open it up, add your stuff, and send it off to these 3 other folks? Sure. So sometimes they may turn on and track changes, sometimes they might not. But now we have this crazy spider web of Word documents flying around, and they're all named things like, Proposal 06, JDH version 1. And then someone like Lisa might get, Proposal 06, Lisa-4. And so these, 15, this is a version control problem. And I know all you guys are well familiar with the problems of version control and what it solves. So, so what I do is create an SWeave file, and I throw it in a Subversion. And I don't even know if Subversion is the hip thing anymore or not, so hopefully you guys will have some insight on that. So that I can start just typing my report and doing the analytics directly in the SWeave file. Because I use Emacs and ESS, so I can kind of have it all right there. And it stays in the repository. I can track the changes. I can put repository tags in my actual document. And once I produce the LaTeX file, I just have to type PDF LaTeX, and poof, out comes a pretty looking PDF file that has built-in table of contents, it has hyperlinks, it has a bibliography that's automatically generated for me. And so the next step for something like this is, if you have to do it consistently, is just make a report. And it goes through the make file and generates the SWeave, or generates the LaTeX documents and all that kind of stuff. So I start off with LaTeX, and so we're going to circumnavigate back to the Lorax and the Onceler. So here's a really basic LaTeX document if you haven't seen one. So we've got some header information here with the markup, make title. Here's a really basic letter, and this is essentially the message of the Lorax from 1971. Right, you end the document, type PDF LaTeX, and poof, a la peanut butter sandwiches, you get your PDF. You can lick the envelope, stuff it in the mail, or email it. Which is all fine and dandy, but I need to include some analytics code in there. Okay, so here is a little chunk of our code that connects to the database. Right, so there's the connection string. Go send the query to the database, fetch all the rows, and disconnect. So now, inside of my SWeave document, I have a data frame called approved acres that has all of the pieces that I need to do analysis when I want to put numerical values into my document. So here's what an SWeave document looks like. for this example. So we've got the basic LaTeX part, right, where the Lorax speaking for the trees to the Onceler. Here's some other code that we've got in there, and these little tags in here. Oh, excuse me. And this, these tokens here for when to start processing our code and when to stop processing our code are in here. So this is a way to stick your R code directly in a LaTeX file so that you have access to it when you need it. And so then, in your actual text, you can go down and do things like, here's my S expression for the percent cut, blah, 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 and produce a document that looks like you sat there, typed it manually, cut and paste, right? Because we can all recognize cut and paste problems in a heartbeat if it's not formatted perfectly. And so LaTeX takes care of all the formatting for us. So here's the process in a nutshell. You open up Emacs, you start typing your analysis letter, you run sweave from within R, okay, and then you quit, and then you run LaTeX, and then out comes your letter. So this is the kind of, let me show you what an example here of what that might look like. Okay, so and I just threw this together a couple of days ago, which is funny because I couldn't lie because the actual date that I did it is in there. So this part right here came out of the database. So this should not change. Here is a, it's kind of hard to read. But the letter itself is horribly crafted. I don't know, I'm not supposed to do this. Don't do it anyway. Let's see here. Okay. So here's what this letter looks like. Here's what the code for this letter looks like. I have all kinds of comments. We have formatting. I include things like, hey, I'm going to take, what is that? 1 million, 10 million random, normal, generated random numbers, format it using an S-printf statement, and throw it in there, and do very tongue-in-cheek analysis directly in the letter as I'm typing. So here I go and grab stuff out of the database and then format it for the contact that I'm sending it to. Whoops. And that, okay. So, it kind of looks like a way to make a really brainy spam machine. So I don't know if that's the takeaway message here, but that's definitely one of the possibilities. So, as I was kind of going through this, I thought, well, yeah, okay, most of these things are possible. This is not even close to being an operational kind of system or weapon or whatever you would want to call it. But I've written a book with Andrew Robinson at the University of Melbourne on doing forest analytics with R. I was in the Use R Springer series. So I think it's possible. I think it's totally possible to create an open source, borderline bomb-proof geospatial analysis stack. For me, I'm being specific to forestry, but it could probably apply to other fields like fisheries. I believe that there was a distro for oceanography a few years ago. LaTeX and SWeave are really great for doing literate programming. Can we do audit-compliant, court-ready sort of processes? I don't know. This hasn't really been tested on that kind of thing. And if you can build it on open source software, you can pretty much build it anywhere. So hopefully we're cool on time. Thank you for listening to me. Thank you for having me here. Thank you for being here. So. If you want to email me or contact me about this, I'll be hanging around. If you see me, let me know. Thank you. I'll stop talking now.